Okay, today we're going to deal with one of the most important topics in the SAT math, which is equations. Well, equations and solving equations is our topic for today. How to solve equations, what techniques, what strategies can we use to solve equations effectively. We'll start revising linear equations, then we'll see some of quadratic equations as well, and then we'll see systems of equations or simultaneous equations. Let's begin. Talking about equations, some important aspects of the theory of equations you need to get acquainted with is how to effectively combine like terms, that is simplifying or reducing like terms. For example, take a look. We talk about like terms when we say, for example, algebraic expression, a monomial, such as, for example, why do we say they are like terms? Because these two algebraic expressions have the same variables and exactly the same exponents for each of the variables. Exponent 2 for variable A, exponent 1 for variable B. So they just differ in the coefficient. These are like terms and these can be operated. For example, you can add them or subtract them. That is like terms, okay? What are not like terms? For example, 8x and 5y. These are not like terms because they don't have the same variables. Okay, so we'll talk about that. We'll also talk about how to square correctly some algebraic expression and taking the square root or square rooting equations. Then we'll see how to cross multiply fractions to simplify algebraic expressions, the use of factoring and factoring identities, how to deal with big algebraic expressions, then how to use this idea of not solving variables individually, but trying to focus on whole expressions when we are requested to do so. Then how guessing and checking, which is also called sometimes ballparking, is a good idea, especially in difficult questions. You can always use the answer choices, A, B, C, D, N, like some inputs that you can use to try to get to the correct choice. Then two more techniques, okay? All of these we'll see today about equations. So talking about the reduction or the simplification of like terms. How do we do this? Take a look at this example. We have if 2 times that sum in the parentheses equals the other sum, find the value of A. How would you do it? Okay, 1 minute to do so, or to try to solve it, okay? Okay, how to do this? The idea is that you notice that when you do this multiplication, new terms appear. Take a look. Plus 6D, multiplying, you know, the distributive property, right? 2 by any or each of the terms in the sum in the parentheses, you will get this. But then you can clearly notice that against the terms that are on the right side of this equation, yeah, they are like terms. For example, this can be simplified with this, this with this, this with this. And what do you get? 2a plus 2 equals 3a. So that means that a must be 2. All right? So you need always to be on the watch to simplify like terms first, because simplifying like terms will make all expressions much simpler. All right, so let's try now another example. Now, when we talk about taking the square of an algebraic expression and taking the square root, we need to do this carefully, right? If this is true, this equality or this equation, the square root of a times b equals a minus b. We know that a and b are positive. The equation above is equivalent to which of the following? How would we do this? one principle when solving equations is that any operation you do on the left side of an equation, you have to do it exactly the same on the right side. And that also applies the operation of raising a number or an algebraic expression to a certain exponent or a power, right? Taking powers. So if this is true, then in order to get rid of the radical, that is the symbol of root, the radical, I need to take both sides of the equation to the power of 2. That's intuitive because when we check the answer choices, we don't see radicals in those options. So we need to get rid of the radical. How do we do that? By squaring both sides. Okay, if we square both sides, what happens? Okay, when you square both sides, be careful. This one doesn't yield this, a squared minus b squared. It is not like that. When you square this, you need to use the identity of the square of a difference. What does it say, this identity? This expression is, or it opens as the square of the first term, take away 2 times the product of the 2 terms plus the square of the second term. This trinomial is the square of a minus b. And this equals, okay, what happens when you square a square root? Whenever you square a square root, it's always the same. You get the radicand here. It's like saying this and this symbol, they cancel each other. Okay, you always get the radicand. So if we square the square root of a times b, we get simply a times b. And from this, we detect that on both sides of this equation, there are 2 like terms. What are the like terms? Well, the like terms are the ones that have the same variables with the same exponents exactly. So what are these like terms? This and this. So we need to simplify the expression, right? If we simplify this, okay, you can take perhaps this to the other side, no problem. So you have AB, 2AB equals a squared plus b squared. So what happens here? This sum is, because this is like you had a 1 here, right? 1 plus 2, 3AB. And this equals a squared plus b squared. So the correct answer choice, option D. Any questions, please? You need to be careful not only with squaring, okay? Squaring expressions. Also, when you take square roots, and here is where something interesting happens. Let's see the example that follows. Okay? It says, if the square of x plus 3 equals 121, what is the sum of the 2 possible values of x? Let me ask you a question. A very easy question, perhaps, for many of you. If you have this, let's simplify this situation a bit. Y squared equals 9. What is the solution to this equation? Let's say the solution is here. Y equals what? You can do it mentally, perhaps, right? What is the solution? Take the square root. Good, you are focusing on the methodology. It is true, actually, that in order to get closer to the solution, you need to take the square root on both sides. Okay, great. Let's take the square root, and this must be equal to the square root of this. People, what is the result? What is the square root of this? Is it y? Yeah, several of you are saying that y equals 3. Yes. Most of you agreed that y should be 3. But take a look. It is true that 3 is one of the solutions, but isn't it true that y could also be negative 3? What happens if you square -3? Yeah, that is 9 too, right? Okay, what is actually the square root of y squared? Some people do this, huh? Take a look. They say, look, what I do here is take the square root of y square. And this is simply y. They say this, cancel this, and you get y. And the square root of 9, they say, oh, the square root of 9, easy, plus or -3. And so from this, you get to the two solutions. What is incorrect in this reasoning? There is a simple mistake here. I don't know if you can see it or not. First, the $1 million question, okay? $1 million question. This expression, a square root of a. This is a square root. A square root can be positive or negative, or can be both. Did you know that the square root of a number, this is a function? Let's say f of a equals the square root of a. How do we graph this function? This function is half of the horizontal parabola. Let's say this is a, this is f of a. What is the square root? Is this. This is the square root curve. What does it mean? That the square root, first, it can only be applied to a positive number, numbers on the left side of the horizontal axis. What else does it mean? That the result of the square root can only be positive. Okay, if this is a, this value here is f of a. The square root is always a positive number, mathematically speaking. So how come the square root of 9 can be -3? Impossible. The square root of 9 is only 3. Okay, I understand, teacher, say some people. The square root of 3 should be 3. Okay, according to this mathematical definition of the square root function, and from where the operator, the square root comes, the square root of any number, positive, any positive number should always be another positive value. So how come the square root of y squared is only y? So where does the -3 come out as a solution? Well, it's simple. This here is never y only. Please don't forget this fundamental identity will come back in a further lesson, in a posterior lesson, we'll come back about this equivalence. This is a universal equivalence. The square root of any algebraic expression z squared, look, this is different from this, huh? It's not this, the square root of z up to 2. No. We're not talking about this. We know this is always z. Now we're talking about the square root of a square of something. This is always the absolute value of z. All right? It cannot be any other way. Why? Why? Think about this for a moment. You know that this expression is always positive. As such, it has a square root because only positive numbers have a square root. The square of z is always positive, but what about z? Do you know the sign of z? Do you know whether z is positive or negative? You don't. Because you don't know, then you couldn't say that, for example, imagine that z is a negative number. And if you say the square root of z squared is simply z, being z negative, that would mean that you are affirming that the square root could be a negative number, and that's impossible. Impossible because of this definition. The square root can never be negative. So we cannot simply say, happily say, that the square root of the square of z is simply z. You cannot just cancel the radical and the exponent too. No, what you need to do is to be aware that this number is positive. the square of seed, but seed itself could be positive or negative. Since the square root always has to be positive, then you take the absolute value of seed in order to positivize seed. So that's the way this algebraic identity works. The square root of any square of something is always the absolute value of that something. So applying this identity in our basic equation y squared equals 9. What is the square root of y squared? It's simply the absolute value of y. The absolute value of y is equal to 3. But what does the absolute value mean? It's the distance of y to 0 on a number line. For example, 0 is here. Imagine y is here. Okay, this distance between 0 and y is always positive distances. This is the absolute value of y. And what happens if y were on the other side of 0, that is to the left of 0, y here? Okay, again, this distance between y and 0 is the absolute value of y. So the absolute value is the positive distance between any number and 0. If the number is positive, that is to say, if y equals or is a number greater than 0, then simply the absolute value of y is simply y, and y equals 3. But if y is a negative number, then the distance between y and 0 would be the inverse additive of y, that is to say, negative y. If y is negative, negative y must be positive, right? Yeah, so negative y is what would be equal to 3. So you have y equals 3 or negative y equals 3, which means actually that y equals negative 3. So these are the two solutions of this equation. But this is the correct sequence of reasoning, okay? Don't say that you take the square of y squared, that is y, and the square root of 9 plus or minus 3, because that doesn't exist. Maybe it's a trick for solving fast, but conceptually it's wrong. So be careful. Now, what is the sum of the two possible values of x? If we understood this explanation, then what would be the answer to the question? We can simply solve this in a very simple way. Take a look. We might say, okay, if I take the square root of this, in order to simplify, what do I get? I get the square root of 121. What is the square root of the square of something? That is the absolute value of that something. And the absolute value equals the square root of the other number, which is 11. So they are telling us that the absolute value of x plus 3 equals 11. That means if x plus 3 is positive, then the absolute value of x plus 3 would simply be x plus 3, the same number. And this would equal 11, from which, of course, x would be 8. But if x plus 3 is less than 0, which may be possible because we don't know x yet, if x plus 3 is less than 0, then the absolute value of x plus 3 would be the inverse additive of x plus 3. That is, x plus 3 multiplied by negative 1. And this would be equal to 11. From this, you can clearly see that x plus 3 would be negative 11, and x would be negative 11, take away 3, right? So the value would be negative 14. The two solutions, 8 and negative 14, what is the sum? 8 minus 14, you have negative 6 for an answer. All right? So that's the answer to this question. Don't forget this, whenever you have to solve a quadratic equation like this. Okay, here what is another possibility? Another possibility is saying this. Let me erase this quickly. Okay, what is another possibility for solving the equation given? You can simply say x plus 3 square equals 121. So x plus 3 equals plus or minus the square root of 121, or plus or minus 11. If you equate x plus 3 to positive 11, you get one solution. If you equate x plus 3 to negative 11, you get the other solution. That's also a practical way to do it. But you know, the procedure shown here is actually conceptually correct, okay? From the mathematical point of view. You need to be clear about this, otherwise you will be making mistakes when working with squares of algebraic expressions. Now, when do we need to cross-multiply fractions? For example, how to solve the value of x here? If 4/5 of x equals 10 over 3, what's the value of x? Can you tell? What can we do in order to isolate the value of x? Okay, so let's see. You can do this cross product, cross multiply. You could say this is like saying 3 times 4x, get 12x, 5 times 10 equals 50. You can simplify a little bit, divide by 2, you get 6, divide by 2, you get 25, and then x equals 25 over 6. Okay, cross multiplying whenever you need. Okay, you can, in this way, you can quickly get rid of the denominators. What about the second example? This time the fractions involve algebraic expressions, especially in the denominators. What's the value of x if this equation is true? We want to combine these two fractions in just one expression. You can try and do this first. You can accommodate the terms, right? You can accommodate the terms like this. 5 over x minus 2 equals 3 over x plus 2. And here is where you can apply the cross multiplication, like this. So you have 5 times x plus 2 equals 3 times x minus 2. Then open the parentheses, 5x plus 10 equals 3x minus 6. Simplify like terms, 5x minus 3x equals negative 6, negative 10. So 2x equals negative 16. And of course, x would be negative 8. Okay, let's see some more cases. Now, when do we use factoring? Okay, or factorization, say other people. We have this expression, b equals a over 3a plus c. Notice that in this expression, 3 variables or 3 letters appear, a, b, and c. But notice that a appears twice. Now, the question is, which of the following expresses a in terms of b and c? Yeah, some can say, okay, a equals b times 3 plus c, that's it. No, but this is not in terms of b and c because a appears again here. You have to get to an expression where a is on the left and on the other side only b and c. One of the 4 answer choices. Okay, you can try. Look, if I want to isolate a, then the key is factoring, okay? First, we propose to do this operation. If you do the cross product, first get rid of all denominators. In order to do that, you can do the cross product here. So a equals actually b times 3a plus c. But for you to isolate a, you need to have all the terms that possess a as a factor on just one side of the equation. And here you see that if you develop these parentheses, you will have 3 times ab plus bc. So there appears a new term that has a as a factor. And because there is another a on the left, you need to put together those two terms containing a on one side so that you can have or extract A as a common factor. So if we do this, take a look. A take away 3A times B equals BC. What have we achieved? We have placed all the terms that have A as a factor on just one side of the equation. Now we proceed to factor the common term. You know, A is a common term in these two terms. A common factor, sorry, in these two terms. So you take it out. Use this, the inverse of distributive property. If x multiplied by y plus z equals x times y plus x times z, you always use this in this sequence or this direction. Now try to see it the other way around. If you have a sum of two algebraic terms or expressions that possess a common factor, you can take this factor out and express the sum or difference of terms as a product. Okay, so let's do that. Take out A out, and you have A multiplying 1 minus 3B. Because A times 1 equals this. A times negative 3B equals this. So it's already factored, and now we are ready to isolate A. Divide both sides by this term, and you have BC over 1 minus 3B. This corresponds to option A. Okay, so that's it. Let's see some more examples. Let's see this question. We have x up to 4 plus 3x cubed plus x plus 3 equals 0. What is one possible real value of x for which the equation above is true? Okay, don't worry too much. This is too much. Some people may say, how come that we are solving equations with, you know, the variable with exponent 4? Are these like quartic equations? No, no, no. You don't need to know how to solve a quartic equation in order to do this. Just be on the watch for opportunities to factor some common terms. Okay, you can try. Do you see some similarity between these two terms and these two terms? Do you notice that there is this pattern? Here only x, here a number, here just x, here there is the 3 again. So what happens if you take the common factor in these two terms? If there is a common factor here, of course, you can say a common factor could be x, right? But also x squared. Okay, if you have two terms that you wish to factor, why don't you look for the monomial or the algebraic term that has the greatest exponents possible? For example, x has as a greatest exponent, sorry, as the least exponent, not the greatest, the least exponent between 4 and 3, you say 3 is the least or the lesser one. So if I factor x cubed multiplies x and yields x up to 4, and x cubed multiplies plus 3 and it yields positive 3 x cubed. So now that I factor these two terms, you can see that there is a pattern here. You have again a common term in this sum of two expressions. Can I factor again x plus 3? Yes, I can. If I factor x plus 3 multiplies this one here, x cubed, and multiplies 1, because x plus 3 times 1 is just this one here, okay? So now that I factor this as a product that equals 0, then you know something to be true. If you have a product of two or more factors that equals 0, what can you guess or conclude about A and B? the least I can say is that either A or B must be zero, right? Because a product can be zero only when one of the factors or all the factors is zero. At least one factor needs to be zero. So this implies that A equals B, sorry, zero, or B equals zero. And this OR is an inclusive OR. That means both can also be zero. That's the meaning of an expression like this. So if this product of these two terms, these two parentheses, equals zero, is because x plus 3 can be zero, or x cubed plus 1 can be zero. From this equality, what is a possible value of x? Well, -3. And from this one, if x cubed equals -1, then x can be -1. So you have two possible solutions here. So what is one possible real value? You may say -3 or -1. Okay, no problem. Any of that two can be a solution. Well, let's now see some more examples, especially when you have questions in which huge algebraic expressions with a lot of variables appear. Take a look at this one. You have here an equation. It says x cubed plus x squared plus x equals x times the square root of the difference of x and 1 over x divided by m times x plus 1 over x. So what are they asking you here? To isolate m. What is m in terms of x? Can you tell? It has to be one of the 4 answer choices. Okay, you can try. So what's the idea here? Okay, don't get lost in the many times the expression x appears. X appears so many times, 1, 2, 3, 4, 5, 6, 7, 8 times. So if you are thinking of perhaps applying a cross product, like multiplying all of these times this, then that could be just, you know, complicating things. Just think about the whole expression as something like this. Imagine that this is simply something like A, and this here is something like B, and this here is something like C. So what do you have? You have this, A equals C over M times B. If I tell you isolate M, what do you have? Isn't it true that you just do this? Oh, this is A times M times B equals C. So easy, M equals C over A times B. And that's it. Because neither expression A, C, or B contains M, right? They are all based on X only. So I can do this. What is C? C is this part, X times the square root of X minus 1 over X. So I take a look at the answer choices. Which one contains only this expression in the numerator? I see that this one here. What about A and B multiplying in the denominator? That is x cubed plus x squared plus x times x plus 1 over x. Is this one. Here is your A, here is your B, and here is your C. So this is it. Option D. I didn't actually need to develop or expand, for example, the multiplication of n times x plus 1 over x. No need to multiply those terms. Just try to visualize that sometimes big expressions, they are just big, but they don't affect how we calculate a variable, how we isolate m in this case. It is much better to do this trick in order to avoid complicating ourselves with the detail of the big expressions. Okay, let's try now some other approaches. Here there is another example of what to do with an expression that is more complex or bigger. This is an equation, a quadratic equation. What is a solution? For what real value of x is the equation above true? So that is to say, what is a possible solution? But considering that x is positive, okay? It must be a positive solution. Please try this one too. There's something that may have called your attention, right? Is that in this question, there is like one expression that works as a variable. Say, for example, x plus 1, right, in this expression. So what if you create a new variable that is a, for example? Let's say this one here is a. So a squared plus 5 times a minus 24 equals 0. So doesn't this look like, you know, a square trinomial? An expression that you can factor? Not a square trinomial, but a quadratic trinomial. Like you, for example, can say, okay, a plus something or minus something times another factor like this, two binomials like this. You know, two numbers that multiply here give you negative 24 and added give you 5. Which two numbers are those? Two numbers that multiply give you negative 24 and added give you 5. What about negative 8 times 3? Okay, if you say this is negative 24, but when you add them, this is negative 5. So what about if we swap the signs? 8 times negative 3. Okay, negative 24 is the product, but a plus negative 3 is actually positive 5. So these are the numbers. A plus 8, a take away 3. This is the factorization of this trinomial. So you know that a either equals negative a or a equals 3 after equating each of the factors to 0. So now if you substitute, what was a? X plus 1. So x plus 1 equals negative 8 or x plus 1 equals 3. From this one, you get x equals negative 9. From this one, you get 2. Since we're looking for a solution that is positive, this is our answer choice. Okay? Well, let's now keep going. Let's see another approach, which is focusing on whole expressions and not on single variables to answer certain questions. For example, if 3x plus 9y equals 9, what is the value of x plus 3y? Yeah, someone might say, yeah, but I cannot solve x and y individually because I only have one equation. But do you really need to solve x and y to know the value of this? You can simply find the value for this expression by factoring this, right? What happens if you factor this? Isn't this, if you take away the common factor 3, 3 times x plus 3y? So if this equals 9, this number here, this parenthesis, is the same as positive 3. And that's the answer to the question. Okay, so factoring in order to isolate a whole expression rather than individual variables. What about this one here? If x over y equals 3, what is the value of y over 2x? You know you cannot find x and y individually from this equation alone. But you can see that this one can be found from this expression. Can you try? So take a look. You can say this. You know that x over y equals 3. And what you have here is y over 2x. But isn't y over 2x the same as 1/2 times y over x? Same, right? And you know that y over x is simply the inverse of this. If x over y is 3, y over x is 1 over 3, the inverse of 3. So 1/2 times 1/3, this is the correct answer, 1 over 6. Okay, so let's see another or more examples. Now, this one is very interesting. Take a look. This question really looks hard. If x squared times x cubed minus 4 equals 4 up to x, If x is an integer, what is one possible solution to the equation above? Can you tell? Which one would be a correct answer choice? So what's the big idea here? It is not that you actually try and solve the equation. It's really difficult because here, you know what? There is x as an exponent. So it's an exponential equation and you also have x cubed. Very difficult to solve this using mathematical methods. So what should you do? So here is why there are 4 answer choices. Why don't you try the answer choices one by one to see which one fits? Since they are telling you that x is an integer, then you shouldn't try this one because that is not an integer. So I try -1. Does -1 work? -1 squared times -1 cube, take away 4, equals 4 up to -1. Okay, this one here is 1. So it's simply this -1 cube is -1, -4, this is -5. -5 equal to 1/4? No, so this is not correct. Let's try number 1. 1 squared times 1 cube minus 4 equals 4 up to 1. 1, this is just 1, so this is 1 minus 4, -3 equal to 1/4. No. So we have discarded already 3. This must be the correct answer. Why? You can verify it, of course. 2 squared times 2 cubed minus 4. What is this? 4 times 8 minus 4, 4 times 4. And 4 up to 2 equals 16. So the equality is good. That's a way you can proceed sometimes. All right? Sometimes it's just a matter of using the answer choices as data that you can try to see which one fits in the equation. Now, other techniques may include matching coefficients. For example, you are supposed to solve the value of constant b in this equation if x plus a squared equals x squared plus 8x plus b. What's the value of b? Some of you may think, is it possible really to find the value of b? Since here we have like x and also a? Yeah, actually it is. It is possible. Give it a try. So how can we do this one here? This question. What is the idea of matching coefficients? What happens when you actually develop or open these parentheses? If you develop this using the identity of the square of a sum, then this is the square of the first term plus twice the product of x and a plus the square of a. And this is exactly the same as this other trinomial. Notice that the two trinomials have this structure, something like ax squared plus bx plus c. The two trinomials are the same. So what can we conclude? That these coefficients, if two trinomials are the same, these coefficients must be the same as well for each of the corresponding terms. So here we can clearly see that x squared is the same as x squared. We can get rid of this actually, right? Because it is 1x squared and 1x squared. If this is true, then there is a match. This coefficient 8 must be the same as 2a. And this constant value must be the same as this. Okay, if 2a equals 8, we know a to be 4. And if a equals 4, b as the square of a should be 16. And that's the answer to the question. Okay, so that's the idea of matching coefficients. Well, then there is one last technique we can see. This is similar to what we've seen before about, eliminating denominators. Here, though it's different from a previous example. Here it doesn't say the sum or difference of two fractions equals 0. No, it's equal to another constant value. So here we cannot just take one of the fractions to the other side and then do the cross product. So how can we do here in order to find the value of x? You can try. Okay, people, in order to process this sum of two fractions where the denominators are algebraic expressions, you can use this approach, right? What do you do when you want to add these two? One possible approach is to use the cross product. You say A times D plus B times C over the product of these two. So why don't you use the same approach here? You can say, okay, I can do this cross product first. So 3 times x plus 2 plus 5 times x, and divide this over x times x plus 2. And this equals 2. So now you can do the cross product in this way. Okay, so you have in the numerator 3x plus 6 plus 11x, and here you have 2 times x squared plus 4, sorry, here. Okay, let's just 2 times x squared plus 4x. So you can, you know, take everything to just one side. You have 2x squared plus 4x. Here you have 14x. So take away 14x and take away 6, and this equals 0. So now what do you have? A quadratic equation, right? Which you can solve kind of easily or not. Yeah, here it's how, you know, comfortable you feel, right? Operating this. So let's simplify the terms. Okay. Here you have 2x squared negative 10x minus 6. And you can notice that you can actually divide each of these terms by 2. And it's a good way to simplify, because when the coefficient of the quadratic term is just 1, it's much easier to factor. For example, you have this y squared plus px plus q equals 0. Then you just need to look for 2 factors like this, where, for example, here a and b. A times b should be q, and a plus b should be p. So it's very easy. Madeline, a question.
I don't understand where you got the 11 from.
Excuse me?
I don't understand where did the
Oh, yeah,
11
sorry,
come
it's
from.
15. Yeah, you're right, you're right. Here is 15, right? Yeah,
Is
3
it?
times, no, sorry, 5. No,
It's
not
5.
15,
Yeah,
5.
I was
5. You're right,
confused.
you're right. Yeah, I was multiplying 3 times everything, but you're right. So here we should like subtract a different quantity. Actually, it is, you know, 8
It is minus 4, right?
negative 4. Yes, negative
Yeah.
4. Okay, so here negative 8 and here negative 4x. Sorry about that. If you divide by 2, this is just 2. So this is much easier to factor. X plus something times x plus something. Two numbers multiply, giving you negative 3, and added negative 2. Like this, right? So from this, you know that this product yields 0. So this happens when x equals 3 or x equals negative 1. But because the answer must be a positive value of x, this is the correct one. Okay, x equals 3. Okay, so now, before doing some more practice about this, okay, we have some exercises we can practice. But since we're running a little short of time, let's cover first some theory here that we need to, how to say, need to cover today. Okay, just give me a moment to, oh, sorry. Yeah, it got lost screen. Okay, so another example. You have this expression, and we need to find the value of A. Here they are telling you that X is different from -2 over A, and A is a constant. That means that this expression here cannot be 0, okay? It cannot be 0. So they are telling you in advance. So what can we do? You can try this one. Okay, so what can we try here? You know, the same approach, cross product here. So you have 3x times ax plus 2 plus 5 times x plus 1. And this over the product of these two. But once you have this product, this instantly matches the denominator of the other side. And here we can do something easy, right? Simply cancel the denominators. And matching the numerators, you have 3x times ax is 3ax squared plus 6x plus 5x plus 5 equals -6x squared plus 11x plus 5. Now, simplify like terms. Here you got exactly 11x plus 5, same as here. So cancel this and this, and you get this equals to this. If 3ax squared equals -6x squared, this and this cancel, and 3a equals -6. So a equals -2. Okay, that's the correct answer here would be B. So that's one way to get rid of, you know, bulky denominators or the fractions with algebraic expressions. Now, system of equations. Okay, when we talk about system of equation, it's easy, right? You have to solve. Basically, in the SAT, we're talking about systems of two equations with two variables. That's the systems of equations we are referring to. Yeah, it's true that there are three variable systems with three equations, but that's not what you'll see in the SAT. So let's take a look at some basic concepts. You will see questions like this, for example, word problems. Tamika purchases a new mattress for $600, which she will pay for with an initial payment of $150 and monthly installments of $30. Which of the following equations can be used to find the number of monthly installments M required to complete the purchase, assuming there are no taxes or fees? Some questions may require you to interpret, okay, some word statements and translate them into an equation, such as here. Or perhaps you need to analyze whether a system of equations, what would be necessary for a system of equations to have or not to have a given number of solutions. For example, we have this system of equations. It says the system of equations above has no solutions. If A and B are positive constants, what is the value of A over B? How can we try questions like this? Take a look. The important thing is first remember the concept of an equation, an equality between algebraic expressions. The algebraic expressions may have variables with exponents 1 or 2, perhaps, right? When you, for example, read a statement and you want to translate that statement into an equation, be careful how you interpret words. For example, this one, this statement, 2 cars and 3 trucks cost $130,000. What about this equation? Do you think this equation represents well the statement above? If yes, why yes? If no, why no? Why not? What is it missing to say that the equation is correct? A correct representation of that statement. Can you tell? Yeah, for example, you may say, teacher, C has to represent the unit price of a car, and T can represent the unit price of a truck. So 2 times the price of a car plus 3 times the price of a truck, that gives a total price of 130,000. That's what you might more or less understand from this, right? But suppose that C and T represent the unit price of vehicles, of cars and trucks respectively. Considering that is the meaning of the variables, is this equation correct? Or what do we need to know first in order to say that this equation is correct? That's the idea with this question. An extra question to help you reason over this statement. Does the statement imply somehow that the 2 cars and the 3 trucks have the same price among them? Can you tell that from the statement alone, or you don't know? Actually, you don't know. I don't know if the 2 cars are one Toyota and one Honda, or they are exactly the same 2 models of cars and the same brand. You don't know because there is no more than this statement. So perhaps one possible equation to represent this correctly would be something like this. If each variable here represents the price of a vehicle, maybe this equation could be correct if all 5 vehicles cost differently from one another. Yeah, it's possible. So be careful how you interpret statements, okay? Don't assume things that the question doesn't say. Always try to interpret statements literally. Okay, so what about this one? Tamika purchased a new mattress for $600, which she will pay for with an initial payment of $150 and monthly installments of $30. Which of the following equations can be used to find the number of monthly installments M required to complete a purchase, assuming there are no taxes or fees? Which one would you say is correct? It's like she pays in 2 parts, right? First, the initial installment or the initial payment, the down payment, as they say, and then installments of $30. How many installments will she pay? Actually, here it says, right? The number of monthly installments is M. So she will pay $30 M times. N times 30 or 30M is the total money she will pay in installments. So which one doesn't have 30M? Okay, this one doesn't have 30M, 150Ms. This is not good. This is 30M, 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 okay. She will pay 30M in all the installments. But besides the installments, she will make an initial payment. So she will also have paid the installments plus the initial payment. And this is 150. Okay, what about this one? Here is taking away, so this doesn't make any sense. The 2 payments must be added to complete the total payment. Here, no 150. Here is incorrect, and this is the only one correct. Adding the initial payment plus the installments gives you the total money she will pay for the mattress. Okay? Now, simultaneous equations, there are 3 types of them. You actually know the most common case is when you have 2 equations that are fundamentally different, right? The most common case, and you can find a solution for the 2 variables. That is one value for each of the variables that make the 2 solutions or the 2 equations true at the same time. This equation or this set of 2 equations, for example. But there are 2 other cases. For example, what happens when two equations are fundamentally the same? So there are infinite solutions. For example, you may think that these two look different. They look different, but they are not different. Why not? Because if the second equation, I rearrange the terms, take all the variables to the left, says 9x plus 3y equals 12, and then I divide each side of the equation by 3, so what do I get? I get exactly the first equation. So the two equations are the same. That means it's just one equation with two variables, one equation with two variables, provided that the variables represent possibly decimal numbers, then it has infinite solutions. There is a third case. Two equations are incompatible, although they are different. For example, take a look at this. If you think about these two equations, you may say, oh, but the equations cannot be transformed one into the other. So there must be a solution. No, take a look. If I rearrange the terms here, okay, 8x plus 4y equals 13. What happens if I divide everything by 4? Here by 4, here by 4. What do I get? 2x plus y equals 13 over 4. And the other equation says that 2x plus y is 6. So which one is true? Is 2x plus y 6 or 13 over 4? Because they cannot be both true, right? How come the same expression be two different values at the same time? It's impossible. These two equations are contradictory, so they have no solution. Okay, now, how can you know in which case you are? Which case you are facing when you are given two simultaneous equations? Take a look at this. Here is the clue. When you have two equations like this, for example, ax plus by equals c, in general, okay? And dx plus ey equals f. How can you know if you are in the case for one solution? What you need to check is this, that a, this coefficient, and this coefficient are not proportional with this coefficient and this coefficient. That is the coefficients of the other variable. If this happens, if these two are not proportional, these four coefficients are not proportional, then we are here. One solution. Okay, this is the easiest way to check that there is a one solution. Take a look at this example. 2 over 5 equals 3 over negative 1? No. So there is one solution. Now, what happens when you have this, that A over D is actually the same as B over E? Okay, if you have this situation with your two equations, then you are either here or here. How do you know if you are here or here? Okay, it's easy. Once you check that A over D equals B over E, check this, C over F. If C over F is different from A over D, then you are here. If it is not, the other case, do it like this, right? Like an if. If it is a yes, you are here. If it is like a no, they are equal, so you are here. Just one equation. Okay, so this is what you can do in order to know which case you are in. Take a look at this thing. ax minus 3y equals 21 and bx minus 3y equals 11. So for this system of equations to have no solutions, what should we expect? We should expect that when we do this, you know, a over b should be equal to negative 3 over negative 3. So what can we say from here? Okay, it's easy. This coefficient simply equals 1. So if A and B are positive constants, what is the value of A over B? It needs to be 1, because this condition that the coefficients of variable x and the coefficients of variable y must always be proportional, okay? If you have no solutions or you have infinite solutions. So just matching, making this proportion, you can tell directly that the value is 1. Let's see some other cases here. You have this system. Again, if the system has no solution, what is the value of A? Can you tell? Now, this is very convenient because all the equations are in the form ax plus by equals c, right? Very orderly. So you can directly evaluate the coefficients as indicated. What should be true about these two coefficients and these two coefficients? Let's go back a little bit. What did we say? When you are in either this case, infinite solutions or no solutions, this is the complying condition, right? The coefficients of x and y must be proportional. So what can we say about negative a and 4 and negative 12 and 3? It must be the same. So from this, we know that a over 4 equals 4. So a equals 16. That's it. Okay, we cancel the negative signs first, right? So that's the way. It's really easy when you think about the principle. Okay, so how do we solve actually simultaneous equations? The two methods suggested are substitution or elimination. Do you know either or both? Okay, what is substitution? Okay, take one variable in one equation and isolate it. For example, let's do y here. Okay, negative 2y equals negative 5x plus 15. So what is y? Y is 5 over 2x plus or minus, right? 15 over 2. So substitute this in the other equation. 10x plus 6 times 5 over 2x minus 15 over 2 equals 45. And then just solve for x, right? If you solve here, 10x plus 15x minus 45 equals 45. So you have 25x equals 90. Divide by 5, you got 5x equals 18. So you have x equals 2.5. Oh, no, not 2.5, 2.6, sorry. Oh, is that correct? 18 over 5, what is that? It is actually this, right? 3.6. Yeah. 18 over 5 is like 15.5 plus 3/5. So that's it. And then substitute this value in any of the equations. For example, here you have 5x minus 5 times 3.6 minus 2y equals 15. So you have now the way to calculate y, right? Simply take away this, 5 times 3, this equals 18. So simply from this, you have that y equals 1.5. So that's substitution. Elimination is playing with the coefficients. You try to equate the coefficients of the two equations, and then you add them or subtract them so that you cancel one variable. For example, I multiply this one by negative 2. So I have negative 10x plus 4y equals negative 30. And then here you have 10x plus 6y equals 45. So when you add these two equations, this gets canceled. 10y equals actually 15. So y is 1.5. Then you can substitute this value in any of the equations and find the other. So the two of them are similar in, how fast you can solve them. Now, here is an example. You have this system of equations, and if this system has infinitely many solutions, what is the value of m plus n? So again, what's the requisite for having infinitely many solutions? That you can actually convert one equation to the other. Okay, you can see here that the constant term is 8, while here is 32. So the idea is, if I multiply this by 4, I have 12x minus 20y equals 32. And this exactly equals mx minus ny equals 32. So these two must be the same. So you can match the corresponding coefficients. M equals 12 and n equals 20. So the sum of these two should be 32. Okay, that would be the answer.